Today we are going to connect cooling tower fundamentals with practical application and sales positioning. The goal of this session is to build a clear understanding of what cooling towers do, where they fit in HVAC and industrial systems, what technical variables drive performance, and how to position the right solution to the customer. Cooling towers are a critical part of many water-cooled systems. They are not refrigeration machines by themselves, but they are essential heat rejection devices that allow chillers, water source heat pumps, industrial equipment, and process systems to operate efficiently. In this presentation, we will move from the basic principles of heat rejection to tower configurations, selection criteria, key components, installation and maintenance considerations, and finally, how to translate all of that into customer value. By the end of this session, the audience should be able to explain how cooling towers reject heat, understand why wet bulb temperature is the key outdoor condition, distinguish between the major types of cooling towers, review a duty point properly, and translate technical characteristics into value for owners, contractors, and engineers. This is important because in the cooling tower segment, technical understanding builds credibility. But credibility alone does not close projects. We also need to connect tower design choices to the outcomes customers care about: performance, energy efficiency, sound, corrosion resistance, maintenance exposure, and retrofit compatibility. We'll begin with the fundamentals: what a cooling tower does, the key temperatures involved, and why wet bulb matters. Then we'll cover the major tower types and airflow arrangements, followed by components, materials, ratings, and application engineering. After that, we'll touch on installation, commissioning, operations, and maintenance. Finally, we'll focus on the sales side: how to position solutions, address objections, and guide customers toward the right selection. The idea is to move step by step from physics and terminology into application and commercial strategy. Cooling towers are used wherever a system needs to reject heat from a water loop to the outdoors. Typical examples include water-cooled chillers, central plant condenser water systems, some water source heat pump applications, and certain industrial or absorption chiller applications. At the most basic level, a cooling tower removes heat from warm water and rejects that heat to the atmosphere. Hot water comes from the condenser or process loop into the tower. Air moves through the tower, and part of the water evaporates. That evaporation is what removes a large portion of the heat. The cooled water then returns to the system. This is a very important distinction. A cooling tower is not producing cooling the way a chiller does. Instead, it is rejecting unwanted heat. It is the outdoor heat sink for a water-cooled system. That is why cooling towers play such a major role in plant efficiency. When selecting or reviewing a cooling tower, everything starts with three key temperatures. The first is hot water in, which is the temperature of the water entering the tower from the system. The second is cold water out, which is the temperature of the water leaving the tower and returning to the system. The third is ambient wet bulb, which is the outdoor air condition that governs evaporative performance. From these three values, we define two very important concepts: range and approach. Range is the difference between hot water in and cold water out. It tells us how much the water is being cooled. Approach is the difference between cold water out and ambient wet bulb. It tells us how close the tower is getting to the theoretical evaporative limit. A smaller approach means the tower is working closer to wet bulb, and that generally requires a larger tower, more airflow, more fan energy, or higher first cost. That is why approach is often one of the most important and most expensive parts of the duty. A simple heat rejection relationship is also useful. Heat rejection can be estimated from water flow times, temperature difference times a constant. It is a quick way to validate if the selection is in the right range. In cooling towers, wet bulb temperature is the outdoor design condition that matters most. That is because evaporative cooling depends on the air's capacity to absorb moisture. Dry bulb temperature still affects operation, but wet bulb is the main ambient condition that defines how well the tower can reject heat. As wet bulb rises, tower performance becomes more difficult. If the tower size and airflow remain the same, the leaving water temperature will increase. That can directly affect chiller efficiency or process performance. This is why tower selections must always specify wet bulb clearly. Without the correct wet bulb, the selection is incomplete or misleading. One of the most common mistakes in the market is looking only at nominal tonnage and ignoring actual wet bulb approach and flow conditions. This slide shows why location matters. Different cities have different design wet bulb temperatures, and that changes the tower duty significantly. A tower selected for one city may not perform the same way in another. For example, Miami, Fort Lauderdale, Tampa, Orlando, Jacksonville, and San Juan all have different wet bulb conditions. In a hotter and more humid location, the tower has less evaporative advantage, so either the leaving water temperature rises or the tower must be sized more aggressively. This is an important sales and engineering point. Geography changes the selection. You cannot assume the same tower selection fits every project location. Water use is one of the most important operating cost and maintenance topics in the cooling tower segment. A cooling tower loses water in three main ways. The first is evaporation, which is the intended heat rejection process. As a small portion of the water evaporates, heat is removed from the remaining water. The second is drift, which is the small amount of water droplets that escape with the leaving air. This is controlled by drift eliminators. The third is blowdown, which is water intentionally discharged from the system to control mineral buildup and maintain acceptable water quality. The water added back into the system is called makeup water, and it replaces evaporation, drift, and blowdown losses. A key concept here is cycles of concentration. Cycles of concentration are the ratio between the dissolved solids in the recirculating tower water and the dissolved solids in the makeup water. In simple terms, they tell us how many times the minerals in the water have become concentrated as pure water evaporates. Higher cycles generally improve water efficiency because less blowdown is required. However, if cycles become too high, the risk of scaling, corrosion, and fouling increases. So the goal is to operate at a level that balances water savings with long-term system protection. From a customer standpoint, this is not just a technical issue. Water use affects utility cost, water treatment requirements, maintenance exposure, sustainability goals, and overall system reliability. This slide introduces the major tower airflow and configuration concepts. First, induced draft towers place the fan at the discharge. This is a very common configuration because it typically manages airflow efficiently and handles recirculation better. Forced draft towers place the fan at the air inlet. These can be attractive in certain retrofits, low-profile installations, or special layout conditions. Next, counterflow means the air moves upward against the falling water. This often supports compact footprints. Crossflow means the air moves horizontally across the falling water. This can offer easier access to fill and simpler gravity-fed hot water distribution arrangements. Then we have single air inlet versus double air inlet designs. A double-side inlet can reduce face velocity and may help with airflow distribution, sound, and stability, while a single-side inlet may be better for tighter layouts. There is no universally perfect arrangement. The correct configuration depends on footprint, sound, maintenance access, retrofit geometry, wall clearances, and recirculation risk. Here we come to one of the most important decisions in the segment: open tower versus closed-circuit cooler. In an open cooling tower, the water being cooled is directly exposed to air inside the tower. It is simple, effective, and often the most economical solution for condenser water systems where direct exposure to air is acceptable. In a closed-circuit system, the process fluid remains inside a coil, and recirculated spray water flows over the outside of that coil. This isolates the primary fluid loop from airborne contamination and debris. So the trade-off is clear. Open towers generally maximize simplicity and economics, while closed-circuit systems provide fluid protection and system isolation. The right decision depends on the application, contamination risk, maintenance philosophy, water quality, freeze protection needs, and overall system design. The unit shown is a single-air inlet, open-type cooling tower. What type of unit is this? The unit shown is a double-air inlet open-type cooling tower. Closed-circuit systems are especially attractive when fluid cleanliness matters. Examples include glycol loops, process cooling, fluid protection applications, and systems where contamination could damage heat exchangers or downstream equipment. A closed-circuit tower may also simplify the overall system by reducing the need for additional heat exchangers or fluid separation strategies. While the first cost is usually higher, the customer may recover that cost through lower risk, cleaner operation, reduced maintenance, and improved equipment protection. From a sales standpoint, closed circuit is often a risk reduction conversation. It is not just about thermal performance. It is about protecting the customer's process, reducing fouling, and improving long-term reliability. The unit shown is a single-air inlet closed-type cooling tower. What type of unit is this? The unit shown is a double-air inlet closed-type cooling tower. Modularity is another important concept in cooling tower projects. Multi-cell towers allow the system to stage capacity, maintain partial operation during service, and improve redundancy. This is highly valuable in facilities where uptime matters. A hospital, data supporting facility, industrial process, or mission-critical building may not want a single point of failure. A modular system can also make transportation, rigging, and site assembly easier. With VFDs and proper cell control, multi-cell arrangements can also improve part load efficiency. The trade-off is that there is more equipment, more controls, and sometimes a larger footprint. Still, in many applications, modularity wins because it offers flexibility and service continuity. Now let's look at the anatomy of a tower. The main components include the fan and motor, which move air through the tower, the fill or the coil, where heat transfer happens, the spray distribution system, which distributes water, the basin, which collects water, and other support elements like drift eliminators, louvers, access doors, platforms, and controls. Fan drive arrangements may include belt drive, gear drive, or direct drive. Each option has implications for maintenance, efficiency, sound, and service expectations. VFDs add another layer of value by enabling fan turn-down, sound reduction at part load, and energy savings. Two related customer-facing topics are drift and plume. Drift is actual water droplet carryover, which must be minimized with proper eliminators. Plume is visible water vapor, typically seen in cool or humid weather. Owners care about plume because it can affect aesthetics, visibility, nearby surfaces, and neighbor relations. These are not just mechanical details. They can influence permitting, acceptance, and owner satisfaction. Materials of construction are a major differentiator in the cooling tower segment. This is where the conversation shifts from simple cost to life cycle value. Galvanized construction may be suitable for many standard applications, but where corrosion risk is higher, especially with chlorides, coastal exposure, or aggressive water chemistry, stainless steel becomes much more attractive. 304 stainless steel is a strong upgrade for many environments. 316L stainless steel is better where chlorides or harsher conditions are expected. Beyond base material, design details matter. Easy clean spray nozzles, scale-reducing water distribution, sloped basins that reduce stagnant water, efficient drift eliminators, detachable coils, and modular construction all contribute to serviceability and durability. This is a very important sales point. Materials should not be sold only as a premium option. They should be connected to corrosion risk, maintenance exposure, site conditions, and total life cycle cost. In the right application, stainless is not luxury. It is protection against early failure and operating disruption. The features highlighted in red are optional. CTI certification is one of the most important credibility markers in the cooling tower market. It means the tower's published thermal performance has been verified according to recognized standards and procedures. This gives engineers, owners, and contractors more confidence that the equipment can perform as stated under rating conditions. It also helps buyers compare products more consistently. However, CTI certification is not a substitute for proper engineering. A certified tower can still underperform if the site layout is wrong, if airflow is restricted, if water flow is incorrect, or if commissioning and water treatment are poor. So, CTI should be positioned as an important trust baseline, but not as a replacement for good application practice. One of the most common misconceptions in the market is to treat nominal tonnage as if it were the real project selection basis. Nominal tonnage is only a reference point. Real projects must be selected using actual water flow, entering water temperature, leaving water temperature, and design wet bulb. For example, a nominal rating might be based on a standard condition such as 95 degrees hot water in, 85 degrees cold water out, and 78 degrees wet bulb. But many actual projects differ significantly from that standard. A practical screening method is to start with flow, often around 3 gallons per minute per ton in standard comfort cooling applications. Then confirm the desired range and required approach. But the final selection must always be based on the real duty point, not just a headline tonnage number. This is where knowledgeable sales and engineering teams add value. They make sure the customer is buying a tower for the actual application, not just a catalog label. There are several ways cooling towers contribute to energy efficiency. First, water-cooled systems typically operate with lower condensing temperatures than air-cooled systems, which can provide significantly better chiller efficiency. That is one reason water-cooled chiller plants often outperform air-cooled systems in larger or more demanding applications. Second, tower selection affects chiller performance. Lower approach temperatures improve condenser water temperature, which can reduce chiller operating cost. But lower approach also requires more tower capacity, so there is always an economic trade-off. Third, proper tower operation matters. Fan control, cell staging, and water treatment all influence real-world efficiency. Fourth, some systems can use free cooling during favorable outdoor conditions. In shoulder seasons, a tower combined with a plate and frame heat exchanger or fluid cooler can reduce or even eliminate chiller operation for part of the year. This is an excellent commercial discussion because energy savings, operating cost, and plant optimization are major drivers for owners and consulting engineers. To summarize, cooling tower performance is governed by wet bulb and the actual duty point. The right type of tower depends on the application: open or closed circuit, induced or forced draft, counterflow or crossflow, single cell or multi-cell. But tower selection is not only about thermal performance. Projects are often won or lost based on materials, corrosion resistance, sound, maintenance, water use, serviceability, and fit within the site constraints. Technical accuracy is essential because it earns trust. But sales success comes from translating technical decisions into business outcomes. Lower operating cost, lower risk, better maintainability, stronger reliability, and better life cycle value. Thank you for your attention. At this point, I'd like to open the discussion for questions. The most useful discussion topics are usually around configuration selection, retrofit constraints, how to compare open versus closed circuit, how to justify stainless steel versus galvanized construction, and how to evaluate the trade-off between first cost and life cycle value. Those are the areas where projects are often won, lost, or improved.